In this lesson, we're going to cover Unit 8, Acquisition 2 on equilibrium and KEQ. So first, we're going to start by defining what is chemical equilibrium. And when you hear that word equilibrium, you think if something's in equilibrium, it's like balanced. Chemical equilibrium occurs when the forward and reverse reactions proceed at equal rates. And we're going to talk about what that means for a little bit. So this occurs with reversible reactions. The way that you can identify a reversible reaction is it's going to have either two arrows, one pointing forward or one pointing back, or like a double-headed arrow. So this is a reversible reaction, and it means that it can proceed either way. So either it can proceed from left to right, or the products can go back and form those reactants. When this reaction goes forward, dinitrogen tetroxide would break down into 2 moles NO2. It proceeds in the forward direction. We also can have what is called a reverse reaction, and now it goes in reverse. For this reversible reaction to reach equilibrium, it means that the rate of this forward reaction is occurring at the same rate as this reverse reaction. One thing that I want to emphasize, that this is like a dynamic equilibrium. It's not static. It doesn't mean that the reaction is not occurring or nothing is happening. The reaction is constantly occurring. We're constantly forming products. Products are going back to reactants. Reactants form the products, vice versa. This is a continuous process. It is just happening at equal rates. The rate of products formed is equal to the rate in which the reactants are formed. So if these are happening at equal rates, this means that concentration no longer changes with time. So in a previous lecture, we looked at a graph of concentration versus time. I called this our fish graph. So we know that the concentration of the reactants are going to decrease over time. We know the concentration of products are going to increase over time. And this looks like a fish. Well, at this point, where we notice that it starts to level out, This is where this reaction reaches equilibrium, the point at which concentration is no longer changing over time. So this brings us to KEQ. KEQ is what we call the equilibrium constant. The equilibrium constant. Capital K, you're going to see lots of different versions of this. K sub C, this is still an equilibrium constant. For concentrations. So when we use molar concentrations to represent equilibrium, we're going to use Kc. Eventually we're going to talk about Ka for acids, Kb for bases. So know that that capital K represents our equilibrium constant, and then we change our subscripts depending on what we're using to describe that equilibrium. So what we're going to do today is we are going to write what's called an equilibrium expression, and we're going to solve for equilibrium expressions. So the equilibrium expression, the way that we are going to write this is products over reactants, each raised to a power equal to its coefficient. Products over reactants, each raised to a power equal to its coefficient. So KEQ is just simply a ratio, products over reactants, and it is going to tell us which way is equilibrium favored. Is it going to be towards the reactants, or is it going to be towards the products? So it is just a ratio to express chemical equilibrium. Let's start by writing a few KEQ expressions. All right, so let's say this was my expression and you needed to write a KEQ. We'll do this first one together, and then I'll give you guys two to try on your own. So to write the expression, KEQ is going to be equal to products over reactants. We are going to put each substance in brackets. Brackets represent concentration. And then we are going to raise it to the power equal to its coefficient. So a concentration of ammonia squared divided by the concentration of nitrogen. Nitrogen does not have a coefficient, so it doesn't get an exponent, times the concentration of hydrogen. It has a coefficient of 3, so we would raise it to the third power. All right, a few things to keep in mind before you guys try 2 of these on your own. We need to pay attention to the states of matter. Pure solids, which would have an S in parentheses, and pure liquids, which would be an L, are not included. If you have a pure solid or pure liquid in your equilibrium, in your reversible reaction, do not include them in your equilibrium expression. The reason that they are left out is because they don't have variable concentrations. Their concentrations are not going to change. But if we had something like a gas, its concentration can easily change because it's compressible. If you were to compress or change the volume of a gas, that's going to alter the concentration of it. Same thing if we had a solution. We can change concentrations of solutions, but if we had something that was a pure solid or pure liquid, its concentration doesn't vary, so we don't include it in the equilibrium expression. Another spot that students commonly make mistakes is they try to add these two together since this plus sign is here. If you have more than one reactant or product, they get multiplied. So keep that in mind because that is a mistake that I commonly see. So try one on your own. Say we had calcium carbonate plus 2 moles of hydrochloric acid. Reversible reaction producing calcium chloride, carbon dioxide, and water. Alright, so take a second, pause the video, see if you can write this equilibrium expression. So the first thing that I'm going to do is I'm going to look at all of my states of matter. Solids and liquids are not going to be included. So I'm going to ignore my solid and ignore the liquid. Now when I go to write my KEQ expression, it's going to be products over reactants. I have 2 products, so I'm going to multiply them together. Neither one of them has a coefficient, so no exponent. Products over reactants, my only reactant is hydrochloric acid. Since it has a coefficient of 2, we're going to raise it to the second power. We're going to do some calculations, and after you do calculations, you're going to have to make a prediction. When calculating KEQ, if KEQ is greater than 1, the reaction favors the products. That shouldn't be something you have to memorize. That should be something that makes sense. Products over reactants. If you have a higher concentration of products, that means the numerator is bigger. If you have a numerator bigger than the denominator, your answer is going to be greater than 1. If KEQ is less than 1, the reaction favors the reactants. Again, products over reactants. Reactants are in the denominator. If the denominator is larger, a small number over a bigger number, your answer is going to be less than 1. All right, 2 examples for calculations. Calculate KEQ, or we could use KC, because I'm going to give you some molar concentrations. For this reaction. If at equilibrium the concentration of N2O4 equals 0.00140 molar, and my concentration of NO2 is 0.0172 molar. All right, so first thing that we have to do is write the equilibrium expression. So again, it's going to be products over reactants. Each raised to the power equal to their coefficient. Now we can plug in our numbers and solve. All right, so I'm going to take my concentration of the products. It's going to be squared, since it has a coefficient of 2, over reactants. We also want to think about significant figures. 1, 2, 3 significant figures, 1, 2, 3 significant figures. My answer would have 1, 2, 3 significant figures. No units, but you should be able to look at this answer and tell me, at equilibrium, does this reaction favor the reactants or products? In this case, KEQ is less than 1. So it favors the reactants. All right, try one on your own and then we'll be done. So this one we already wrote the equilibrium expression. I already gave you this one as an example. But now let's add the calculations in. All right, so my suggestion is to pause the video, practice writing your KEQ expression, plug in your values, solve. When you're done, unpause the video, come back and see how you did. All right, so we are first going to write our expression, products over reactants, each raised to the power equal to their coefficient. If we have more than one reactant or more than one product, we multiply those values together. Now we just need to plug in what we know. Plug it in our calculator and solve. Alright, when I plug this into my calculator, keeping in mind significant figures, everything has two significant figures, 0.083. And again, here's an example where it is less than 1. So at equilibrium, this reaction favors the reactant.